So we didn't quite finish with the inverse functions, and it's important in this class and in the next one. Well, and very, very important in Calc 2. A one-to-one function looks like this, and you see it's, I didn't even put arrows there. It's just so easy to travel back and forth on it. Now, most functions, especially the trigonometric ones, are very periodic functions, are by nature very, very not one-to-one. The whole thing repeats, right? But mathematicians want functions, always, always, always. For example, inverse sine. You can only have an operation if it's operations by nature should be functions. There should be just one answer. When you ask the calculator what is square root of 9, you don't want to have 3 Monday, Wednesday, Fridays, and -3 Tuesday, Thursdays. I don't think our buildings would be very stable built on that number. So just for the single fact that inverse functions are very often operations, like the square root operation, we want them to be functions, even if f is not one-to-one. So what we do is we minimally restrict the domain. Minimally means we keep as much as possible, but it's a one-to-one. So we restrict the domain until it is one-to-one, then take the inverse. And the example that I gave you was something that's kind of a middle area. You have to memorize what how the domain restriction was done, but it's such a logical choice. F of x equals x squared look like this. The inverse relation looked like this. Remember, we just swapped the coordinates. So if this point here is -3, 9, and this point here is +3, 9, then when you swap the coordinates, you get 9, -3, and 9, 3. And my recommendation was that plotting the inverse, just have a lot of points, swap the coordinates, plot the dots, connect the dots. So use the swap coordinates method. Not one-to-one, not a function. So we restrict the domain. And this is what's not going to be all that trivial in trig, but it is trivial that, well, let's just keep the non-negative half. Here, the original domain was R. The original range was everything positive when 0. Restrict the domain to this. Take inverse. So this is the restricted function. This is the inverse. As you very well know, the inverse of squaring is the square root function, but that's how it was done. The restricted domain is 0, infinity. The range is still 0, infinity. So, but when I said minimally restricted domain, that means we don't want to change the function values. We don't want to lose too much. We just want to sort of lose the x values that cause duplicate of y values. So the goal is to keep the range. It's just every number in the range should be taken once and not twice or infinitely many times. And now in the inverse, we swap the two. So, well, these are the same, so it's not a big deal. But now I'm showing you because this is how it's going to go. If someone asks you, okay, tell me what is inverse sine. It's not a computation, it's a story. We're going to draw the original function with the original inverse relation. Then we're going to restrict the domain, stay the domain and the range of the restricted function, and then take the inverse. So basically, we're going to repeat this story with, let's start with sine. The inverse relation is badly not a function because sine is not one-to-one. So we have to restrict the domain of sine x. We want two things. Number one, we want every value between -1 and 1 to be taken, but only once. And this is the one thing that you have to memorize. And so let's look at the unit circle. Sine is the second coordinate. So we want just one time sine every number between -1 and 1, the sine of an angle. That's the second coordinate of a point on this unit circle between -1 and 1. Any ideas? This will not do. 0 to 180 will not do because we don't have any negative values and the positive ones repeat. But this kind of makes sense and this kind of makes sense, right? And you see here, the y-coordinate of the points are -1, 0, 1. But every value is just taken once. Now, let's put two angles on this point to express this as an inequality. What two angles would you put here?
90 and -90.
90 and -90. I was hoping you say 90 and 270, and then I could say, well, that gives us this range. But -90 and 90 gives us exactly this stuff. Now, it should be understood that we're taking the y-coordinates, don't repeat, and they take every value between -1 and 1. You know how I remember? There are two major characters in trigonometry, sine and cosine. And I noticed that this one is selected, so the other guy is always positive. You see, between -90 and 90, the cosine of all angles is positive, and that's going to be very useful. That was a very, very nice way to select the interval to which restricted. So the only thing that you can memorize, you have to memorize, is that we restrict the domain to -π/2, π/2. Feel free to think 90, -90, and then the range is still should be between -1 and 1. You know, this is going to be important, very, very important in Calc 2. And the funny thing is, this is what we selected. Now, this thing, if you read it left to right, it increases. But we could have picked the decreasing part. And those ambiguities will show up actually in the calculus. You're gonna look at things like, when is it increasing or decreasing? So the fact whether inverse sine increases or decreases, that's not really in the numbers. In a way, we kind of selected the piece that is an increasing piece. And there's three important numbers of points on this 0, 0. This is -π/2, -1. This is π/2, 1. I think it's important that you scale it correctly. So this is about 1.5. This is about 1. So that when you swap the points, I refer to this mental image as a pathetic little sliver. It's like, so just 1/2 of this this shape really, and then 1/2 of this shape. These two don't meet only in the origin, so I kind of messed up the picture. And so we restricted the domain to -π/2, π/2, and the range is still -1, 1. Solve them. So inverse sine x, here is the graph. The domain is the range of the restricted one, -1, 1, and the range is -90, 90. Okay. And so if someone says graph or explain, this is the story. There's no computation. You just have to basically do this story. Until to this day, when I have to come up with inverse sine, I do this. I do it faster, but I just walk this line. The only thing that you have to memorize is the interval upon which we restrict the function. The rest is just, you can figure it out on the spot. You have to understand the difference between compute inverse sine of, let's make it interesting, and let's do -1/2. We did half so much. And solve sine of x equals -1/2. These are hugely different questions because this has how many solutions, this equation? And this is one number. This is two groups of infinite coterminal angles. So two families of infinite coterminal angles. One of them is around negative 30 for coterminal, and the calculator will give you that one. The other one does not fall. You have to come up with that. And it's still the supplement symmetry. So basically, we're going to get negative 30 plus k times 360. That's already infinitely many angles. Okay, you do it in radians, but still. And 210 or negative 150. I like 210 in this case because they still add up to 180. They're still supplements. So it's doubly infinite solutions, because to solve means find all numbers that do that. So to solve an equation, we have to find all of them. And this one is just a single number. So whenever people get this equation and they answer this, ooh, they lose a whole chunk of points. They are related, because how do we define this? We define this as follows: solve this equation and then pick the only one that falls between negative 90 and 90. And that one is negative 30, and your calculator will never make a secret out of it. You can sort of ask the right questions. You can ask inverse sine of, well, I'm going to start with negative 0.5. Well, maybe I should turn it on. Second sine of negative 0.5. It should give you negative 30. And we can ask inverse sine of negative 1. That should be negative 90. So you can sort of ask your calculator smart questions and figure out the range. Not range, the interval, the range of numbers. You have to be the one who remembers the other one, the 210 in this case. So you're not going to mix up the two, right? You're not going to answer this for this question, because then I'm going to subtract a whole bunch of points and then yell at you too. Then I see you next. Okay. You know, I don't like this inverse notation. There is another one, arc sin x. I much prefer that. Actually, my handouts only had that. And then I realized people don't understand the calculator, why that sign -1. So I rewrote them. But I'm having second thoughts. Same thing. And if you want to take the reciprocal, well, you know, to avoid that confusion, cosecant. It has a name. So you have no reason to think that this is reciprocal. For the reciprocal, we avoid using this, even though it would look like sine x to the minus, that's not. And then you need the parentheses, that's even worse. So we just write cosecant. This is when you're traveling backwards. This is when you flip the number. Completely different. Now we're going to rinse and repeat with cosine. So the unrestricted cosine looks very much like sine. So the inverse relation will look very much like the inverse relation of sine. This here is 0, 1, right? So that will become 1, 0. This here is pi over 2, 0. Again, this should be a little longer. This is 1.5-ish. This is 1. And so when we swap the coordinates, we get 1, 0. That point becomes this point. And this point becomes that point. This is 0, pi over 2. And you might need a few other points to kind of get the hang of it. Let's do a few other points, and then we know how to connect it. How about this point? What are the two coordinates of this point?
3 pi over 2, 1.
Negative 1. 3 pi over 2, negative 1. So from that, it's gonna, when we swap the coordinates on the inverse, that's gonna be negative 1, 3 pi over 2. And then let's do this one, and I think that should be enough. This is negative pi over 2, 0. So it's gonna be 0, negative pi over 2. Not a function, because not 1 to 1. So this is 0, negative pi over 2. And that kind of, you see, you squint back, you squint, you take a step back, you see that this is the shape. But you can ask intermediate points, 60 degree, 30 degree, or any angle with a calculator, if you're not sure. But after we're done graphing the inverse relation, the symmetry should reveal itself. I could not use this symmetry, especially for this one. I thought sine was bad. But there it is. There is the symmetry reflective to this. And then the unrestricted cosine x has a domain of, same as with sine, right? The domain is everything. The range is between -1 and 1. Now, so next up, before we take the inverse, we want it to be a function, so we're going to restrict the domain. We want every cosine value between -1 and 1 to be preserved, but only taken once. If you look at the unit circle, now you want a part of the unit circle where the x coordinates take a value between -1 and 1. This one is very reasonable. What would be a good interval to restrict cosine on?
180.
0 to 180.
180 and
180 and 360 would also work. But remember, the way I remembered where the other guy is positive. So it's here. That's going to be tremendously useful later on, because when we have to worry about hideous things like cosine of inverse sine of, I don't know, 1/3, it's always positive. That second part, that migraine headache, we set up the inverse sine so it shoots you into a place where the cosine is always positive. It's going to save so much headache. And there is another reason, which I haven't known for a long time, that I'll also show you. So basically, where the other guy is positive, and that's between 0 and 180. And then it should occur to us like, wait a minute, in a triangle, if we're looking for an angle, those angles live between 0 and 180. Here is another very good reason why we should select 0 to 180. Because very often, with lots of polygons, we chop it off and basically we're looking at triangles. Triangles are simple enough for us to look at. And countless times, we are using trigonometry to find an angle that sits in a triangle. And then why not select the region 0 to 180? So we restrict, and that's the only thing you have to memorize. There's nothing to memorize, just a technique. Restrict the domain to 0, 180, or 0 pi. The range of the x coordinates is still, here it's -1, here is 1, is still -1, 1. Okay. So now I'm going to graph the restricted cosine, state the domain and range, and then graph the inverse, swap those two. Restricted cosine, the domain is 0 to pi, and the range is -1 to 1. And the picture, I usually start with the whole cosine and then just select the part. So 0 to 180, this one is a decreasing. If you read it left to right, this piece is decreasing. It starts with 1 and ends in -1. So what about the points? This is 0, 1 from that, or you can peep into and just select the part. But it's a good practice. 0, 0, 1, cosine of 0 is 1, cosine of pi is -1, and then this is pi over 2, 0. So swap the coordinates. 0, 1 will become 1, 0. Pi over 2, 0 will become 0, pi over 2. Pi over 2 is 1.5, so it's more than 1. So that's 0, pi over 2. And this is pi -1. It's going to be -1 pi. Yeah, I wouldn't be able to do this with reflecting that diagonal line, but now that it's so, this pathetic little sliver, it's going to be so important in calculus. That is the symmetry. And now the inverse cosine x, or arc cosine x, will have a domain of, just swap the domain and the range, but it shows from -1 to 1. And the range of 0 to pi. No competition, just this story, as I told you. And that's what I do mentally whenever I have to record something from here. Any questions? All right, let's tackle tangent. Now tangent x has a shorter period, right? Cosine is 0 here and here. Those are going to be where the denominator is 0, so you get this freaky like 1 over x around 0. That is a very natural way to restrict it. So let's just first, without restriction, so these threads just keep happening. So tangent x, the domain is, well, every number except for when cosine is 0, that's when the denominator is 0, that's 90, 270, or coterminal. And the range is interesting. The range is now everything. How would you restrict the domain given this picture? Well, one natural way is just, can't we just take one thread? Like one of these, we'll just do. It will take every value and every value once. And that was a selection, but which thread would you pick? Which is the most natural thread to pick? I call these things threads. Well, the one that goes through the origin. And so, but before that, it's kind of cute what the inverse relation looks like. I don't want to mess up this picture. I'd rather start moving on. This vertical line has an equation x equals negative pi over 2. And this is x equals pi over 2. And this is x equals 3 pi over 2. Then we take the inverse. These are going to become lines with equation y equals negative pi over 2. Y equals everything, x becomes y and vice versa. So x equals negative 3 pi over 2. And then here is a thread. So what does the inverse look like? Well, these vertical lines are going to become horizontal lines. These vertical threads are going to be somewhat of a horizontal thread. So here is the line, y equals pi over 2. This vertical asymptote will become this. And then here is the line, y equals negative pi over 2. You can use values. You can use the calculator to get a few points. And that's going to be the inverse tangent, the function. But now I'm going to mess up because I want to show you what the inverse relation look like. It's basically, you're just going to keep piling these things up horizontally. So this thing repeats. And this is what the inverse tangent looks like. That's the prettiest inverse function. It's not a pathetically little sliver. It has a perfect domain. It's kind of nice and curvy. Our tangent is really important and pretty, if I may, compared to these pathetic little slivers that inverse sine and inverse cosine are. Unrestricted tangent, the domain, I wrote it somewhere. Oh, there it is. The domain is x is not plus or minus 90 or coterminal, and the range is everything. So we restrict the domain to, now, if you draw tangent, it becomes obvious from the picture that it's a perfectly reasonable answer to pick up just one thread. So to reduce the domain to something like that. And then, of course, let's pick the one that goes through the origin, right? Y between 90 and 270, if we could go with the origin. And so the restricted domain is almost the same mentally sharp tangent next to sine. They're already together in the sense that they're both odd functions, right? Sine of minus alpha is minus sine alpha, same with tangent. But the only difference between the restricted domain of sine and tangent is that this one does not allow 90 and negative 90. So it's an open interval, negative 90, 90. Meanwhile, sine had the closed interval. But that's it. The range is still everything. This is x equals minus pi over 2. This is x equals pi over 2. This is the restricted tangent, just one lovely thread. And then we take the inverse. So this line, x equals negative pi over 2, will become y equals negative pi over 2. X equals pi over 2 will become y equals pi over 2. And you can sort of describe that we're getting closer and closer to pi over 2. Well, that's what's going to happen here. I don't think tangent and inverse tangent also meet elsewhere than the origin, but I'm not that sure. No, I don't think they meet. No, that's going to be my homework. And a vertical asymptote will become a horizontal asymptote. Arctangent, the domain is, well, what was the range? Everything. And the range is what used to be the domain minus pi over 2 open interval. That's how you do that. Now, there are three other functions, right? There is secant, cosecant, and cotangent. You should practice doing exactly what I just did. Just walk the path of, well, here is the unrestricted one. The inverse doesn't work. It's too much. Let's restrict. State the domain. State the range of the restricted. Graph it. Then take the inverse and state the domain and the range. There's not a computation. You should practice that. And I think you should do that with the other, at least the other two, secant and cosecant. And let me just give you an advice. For the restriction, just use what the cosecant is the reciprocal of sine. Restricted the same way sine was restricted. Secant is the reciprocal of cosine. Restricted like you restricted cosine. It's not going to be exactly the same because sine has a perfect domain, but 1 over sine will have issues where sine of x happens to be 0. But pretty much that. And practice drawing, practice this story, at least with secant and cosecant. I don't think cotangent is as important. It's going to be a very similar picture, very similar story. So how did we restrict? That's the only thing you really have to memorize. To invert, that's the verb of taking the inverse. To invert trig functions, we restricted the domain and think for sine and cosine, think where the other guy is positive. Where is the other guy positive? Here. So for sine, it's between negative 90 and 90. Cosine x was defined where the other guy, namely sine, is positive, and that's here. And then you should think, oh, yeah, that's good for angles in triangles. When we look for angles that live in triangles, 0 to pi. And then you have two options with tangent. You either visualize this picture when going from negative 90 till 90 is a very obvious choice, right? You have to pick up thread. Okay, you could pick half a thread, this half and this half, but who would want to do that if you can just pick something nice and symmetrical like that? Or mentally shove it with sine. It's an open interval, but otherwise the same, negative pi over 2 pi over 2. That's the only thing you have to memorize. And you know that namely where the other guy is positive is not just a cosmic coincidence. I think that was intentional. I think that was part of why these things were defined, how they were. You know, inverse sine and inverse cosine of a positive number is easy because that places you in the first quadrant, right? Inverse sine, if the sine is positive, you're in the first quadrant. If the sine x is positive. And you're here if sine x is negative. So it's not a really interesting question. If I ask you about inverse sine of a positive angle, that's in the first quadrant. Same with cosine, right? Here, cosine x is positive. And here, cosine x is negative. But you could say, why was this picked like that? I was perfectly content with where the other guy is positive, and there will be reasons for it, and you're going to be very grateful for that, because certain expressions, we don't have to worry about the sign, which is the most annoying part of trigonometric function values. You know, is it positive or negative? But there is another reason that I want to show you. This, I didn't know it for quite some time. I just know it for a few years now. Grab your calculator and compute this. Inverse sine of 1/4 plus inverse cosine of 1/4. See what you get. This is an exercise on the calculator. You can do 0.25. You get 90, exactly. I got 90. inverse sine of 0.25 plus inverse cosine of 0.25 is 90. Okay, let's do another one. Inverse sine of, I don't know, -2/3 plus inverse cosine of -2/3.
Also 90 degrees.
I also got also 90 degrees. So there is this identity. An identity, you know what an identity is, but that was a strange one to me. Inverse sine x plus inverse cosine x equals to pi/2. Now, what the hell is this? Looks weird. This looks weird. I know I lived decades without this, and I had a lot of math in my life. But in the first quadrant, in right triangle trigonometry, it kind of makes sense. Let's just A, B, C, alpha, beta. All right. Now, let's say, what is inverse sine of A/C? You have to filter through the notation. What is it? What are you asked here? Okay. So this is kind of mathematically a little unjustified, but this works for me. Is think of sine as these are angles and these are ratios. Now, that's not really true because we worked hard with radians. They are both just real numbers.
Alpha, right?
But,
Alpha.
but alpha, exactly. So whenever you see an expression like that, ask yourself, what is this? Is this a ratio or is it an angle? That would be my first. And once you realize, okay, this in sine, forward sine will take you from an angle to a ratio. Inverse sine does the opposite. So we should come up with an angle. What angle? Well, the one whose sine is A/C. So it's notation that's really hard, but I remember it made it difficult for me. I still remember that. Basically, the question is, find the angle whose sine is A/C. So now you're looking at this triangle and say, okay, A/C is the sine of which one, alpha or beta? A/C is sine of alpha, right? And if I say cosine inverse of A/C, again, you have to find an angle whose cosine is A/C. It's beta. A/C is sine of alpha, but cosine of beta. And so the statement inverse sine of A/C plus inverse cosine of the same ratio is basically alpha plus beta. And in a right triangle, that's going to be 90 degrees. It's kind of an obvious thing. Once you think about it, you remember that cosine means the sine of the other. So basically, it's asking you to add the two other angles in a right triangle. Does this make sense? Why this is true? I'll take your silences. Yes, it's crystal clear. Now, I believe that part of the decision was that this identity, turns out it's pretty important one, that this should still be true after we defined inverses of negative numbers. So inverse sine of half. No, half is easy, minus half. And inverse cosine of negative half. Let's figure it out. So where is sine negative half? Well, -30 and I said 210, but that's not going to work, right? It's the inverse is picking where the cosine is positive. This is the inverse sign, where inverse sign lands you. So it's -30. And that's for that, right? You have to solve the equation. Sine alpha is -half. The answer is -30 or coterminal or 210 or coterminal. But then you have to pick the only one that is in the first or fourth quadrant. And by the way, you can ask the calculator too. So obviously you're not going to get points because you have fingers. So you're going to have to at least pretend to work around it, but there it is. Now, inverse cosine of -half. Well, here is cosine equals -half, right? It's, I would say ±120. Because that's a symmetry of cosine. But we have to pick the one that falls into the standard where we decided to restrict the domain of the original cosine, which is then the range of the inverse. I still have to kind of go through that. It's the one that, you know, it could be an angle that lives in a triangle, or where the other guy is positive, it's 120. And when you add these two, you still get that 90. And I think that was part of the decision. So sine inverse of minus half plus cosine inverse of minus half equals 90 is still true. And that's going to come up, that you have two functions, and when you add them up, you get a constant. These are functions with different graphs, different domains, oh my God, but when you add them, you're going to always get a constant. Well, here is the explanation. There is a reasonable explanation in the first quadrant, right triangle trigonometry, and then the way we defined inverses for negative numbers, well, we had it in mind that this should still be true. Okay, any questions?